The Midcontinent Rift Zone in North America could become a massive natural hydrogen production source, supporting the global demand for clean energy. About 1.1 billion years ago, the North American continent nearly split in two, leaving behind a 1,900-kilometer-long volcanic rock formation known as the Midcontinent Rift Zone. Researchers from the University of Nebraska-Lincoln are studying this rift, which stretches from beneath Lake Superior through parts of Minnesota, Michigan, Wisconsin, Iowa, Nebraska, and Kansas, to determine how best to access the vast amounts of hydrogen it harbors. SciTechDaily reported on November 15th. Hydrogen could play a pivotal role in reducing reliance on fossil fuels. It is carbon-free, and unlike oil and gas, which take millions of years to form from organic sediments, hydrogen is continuously generated underground as water interacts with volcanic rock. To test hydrogen production potential within the rift, scientists drilled a test well in Nebraska 5 years ago. The data so far is promising. The team believes that the geological and biogeochemical conditions of the rift may have prevented significant hydrogen loss, preserving it at economically viable levels. This area might be deep enough to store hydrogen, but still shallow enough for us to access. The geology is working in our favor, said Carrie Weber, a professor of atmospheric, biological, and earth sciences. The U.S. Geological Survey, USGS, estimates that tens of millions to tens of billions of megatons, 1 megaton equals 1 million tons, of hydrogen exist within Earth's crust. However, much of it is inaccessible because it lies too deep, too far offshore, or in concentrations too small for extraction. This makes locations like the Midcontinent Rift Zone particularly valuable. Other underground rifts worldwide, including in France, Germany, Russia, and Africa, could also serve as potential hydrogen sources. The Nebraska team is investigating several key questions, such as how hydrogen flows and migrates to the surface, the potential for natural storage or engineered storage systems, how hydrogen interacts with underground fluids and minerals, and the extent and rate at which microbes consume hydrogen. According to Seung-Hee Kim, a professor of civil engineering,